Okay, so let us start. So yesterday we just looked into the basics of mass transfer, isn't it? Just the basics of mass transfer, how things work. Then we covered very basics like molar concentration, mass concentration, velocity concept, that molar average velocity, mass average velocity. We got an idea about what is our conductive diffusion, convective diffusion, and our advective diffusion. Okay. Then how to increase the rate of diffusion. Okay. Then we came to the general equation or the fundamental equation of mass transfer, under which we covered what is our flux when our observer is stationary and what is our flux when his observer is moving at average molar average velocity. Okay. Then we also covered the like the concept of diffusion velocity, and till here we have done. Okay, till here we have covered. So from here we were saying that our this thing, what to say, this diffusion can be of three types. So we were considering one is diffusion of A through non-diffusing V, equimolar counter diffusion and unequimolar counter diffusion. So from here, the part that will be important for you in the GATE exam will start. Okay, from here like numericals will be arising. So let us see. So see here. So what is the general equation of mass transfer? It is Na is equals to Nt into Xa and plus Ja. Okay. Now before that, let us understand one more thing. That what is our Ja? Let us understand one more thing. That is what is our Ja. So Ja is nothing. It is given by minus Dab into dou Ca by dou Z. Okay. Now this is known as, everyone will be knowing this also. This is known as your fix. One second. This is known as your fixed first law of diffusion. Okay. Fixed first law of diffusion, which just states what is that flux is directly proportional. Flux is directly proportional to the concentration gradient in that direction. Like what is happening is that suppose you consider flux in z direction, so this will be directly proportional to dou Ca minus dou Ca by dou Z. Okay. Yeah, concentration gradient means nothing, just concentration with respect to your space. This thing we covered yesterday, no? That what is your rate and what is your flux? What is your rate, what is your flux, and what is your gradient? So rate is any quantity per unit time, and flux is any like rate per unit area, and your gradient was any quantity per unit space. So this gives you your concentration gradient. So concentration per unit space. Space means nothing, just distance. So Z here will just represent your distance. Okay. So this is the formula. This is the formula for your fixed first law. Okay. Why this negative sign? So this negative sign just represents as our like concentration is flowing from high concentration to low concentration. As the solute like transfers from high concentration zone to low concentration zone, so that is just represented by this negative sign. Okay, so this is the directly proportional sign. So you know that for removing a directly proportional sign we need to use a constant of proportionality. So just the constant of proportionality we use is known as your dab, and then this becomes minus dab into dou Ca by dou Z. Okay, now this dab is known as your diffusivity, or it is also known as diffusivity coefficient. Okay, so this diffusivity. So let us do a little bit of unit balance. Okay, what is the unit of flux? J is flux, no? So what is the unit of flux? It will be mole per meter square second. This we have seen yesterday. What is the unit of your this Ca? It will be mole per meter cube. And what is the unit of your Z? That is your distance, so meter. So this will just become mole per meter to the power 4. Now please understand, if this and this is this equation is dynamically correct, then this unit and this the unit on the left hand side must be equal to the unit in the right hand side, isn't it? See like from here many concepts you will be getting. Okay, please understand. If any equation is dynamically correct, then the unit in the left hand side will be also equal to the unit in the right hand side. Okay, this concept will also be used in your CRE while using like mixed order reactions, no, where the order of reaction minus Ra is like suppose K1 into Ca plus K2 plus K3 Ca square, like this. These type of reactions are known as your mixed order reactions. So in this mixed order reactions also, no, like if you have been suppose it may happen that in the question you have been said to find out the unit of K2 or the unit of K3 or the unit of K1. So there also this concept is very useful. It is known as dynamical. The units and dimensions, no, that in class 11 we have covered. So the same concept. So for any equation to be dynamically correct, the unit in the right hand side must be equal to the unit of the left hand side. So the left hand side unit is mole per meter square second. Okay, very good. The unit of flux. Now let us derive the right hand side unit. The right hand side unit dou Ca by dou Z, it is mole per meter to the power 4. What is the unit of diffusivity? So let us just equal it. So mole will cancel out. This meter square will make it meter square. And this will go this side. So we will be getting meter square per second, and this will be the unit of your diffusivity DAB. Okay. This will be just the unit of your DAB, that is your meter square per second. Clear? So now let us understand that what this unit signifies. What this unit signifies. What this unit meter square per second signifies. We can write it as meter into meter per second. Okay. Now please understand from here very carefully that this meter represents your mean free path or distance traveled by the solute, and this meter per second just represents the velocity. So that's why we say that whenever the mean free path or the distance traveled by the solute increases, our diffusivity increases. And we also say that if our velocity increases, then also our diffusion increases. Why? Because velocity increases or mean free path travel increases, then our overall diffusivity will increase. And if diffusivity increases, then diffusion will also increase, or rate of diffusion will also increase. Clear? As because if DAB increases, then your flux will be increasing. Now, flux means nothing, just rate per unit area. So once you multiply your flux with your area, then you will be getting your rate. So if flux is increasing, your rate will also be increasing. And for flux to increase, your DAB must increase. And for DAB to increase, just now you saw that either your velocity must increase or your mean free path travel or distance travel by the solute has to increase. Okay. So that is the physical significance of this unit of meter square per second. Clear? So this was like a basic thing only. So this we must be knowing. Now we will just go into the derivations for different cases, and we will just write down the formulas. Okay. Like in detailed derivation, we will not be going. We will just write down the formulas and we will move forward. So till here, I hope it is clear. Okay. If till here it is clear, then we should move forward. Just check it once. I'm just showing it to you. Okay, from here. Okay, chalo. Yeah. So what was our general equation of mass transfer? So it was Na is equals to Nt into Xa and plus Ja. Or you can write it as Na is equals to Nt into Xa and plus, instead of Ja, now you have got the expression for Ja for the fixed first law of diffusion. So you can directly write minus Dab into dou Ca by dou Z. Now how many conditions were there? The first condition was diffusion of A through non-diffusing B. So diffusion of A through non-diffusing B means that our Na will be there. That is, our A is diffusing. However, our Nb will be equals to 0 because B is not diffusing. For example, you can take an instance that suppose you have kept a beaker. Okay, this beaker is full of ammonia. So ammonia vapors will get generated, and suppose here air is there. Okay, suppose here air is there. So these ammonia vapors will diffuse in the air. Okay, let ammonia be component A and this air be component B. So what is happening here? These ammonia vapors are diffusing in the air. That means Na will be there. However, this air is not diffusing into the this ammonia vapors. Like this air is not getting diffused into this ammonia vapor or into this beaker. So our Nb is equals to 0. So this is just a simple example of your diffusion of A through non-diffusing B. Like B is not diffusing, however A is diffusing. So in that case, what will happen is that our Na will be is equals to Nt is nothing but Na plus Nb. That is our total flux. We are all considering it for a binary system. Please remember, we are just considering it for binary system. So Na plus Nb, and into for like let it be like a gaseous phase. So let us write the mole fraction as Ya and minus Dab into dou Ca by dou Z. Okay. Just from here, what you do, your Nb is equals to 0. So that will be equals to 0. You take Na common in the left hand side. This will be is equals to minus Dab into dou Ca by dou Z. Okay. This derivation you will get in any book, so not required to focus on it more. So this will just become Na is equals to minus Dab into divided by 1 minus Ya. Okay. And this dCA also you can convert now. Like Ca will be is equals to Pa bar by RT. Okay. So first convert this into this. So this will become dou Ca by dou Z will be is equals to 1 by RT. RT is constant, and dou Pa bar by dou Z. Clear? Now see here. Your Pa bar is equals to your mole fraction into total pressure. So just put it in the formula. This will become 1 by RT into dou Ya into Pt divided by dou Z. Now total pressure is constant, so this will also come out of the derivative. So this will become Pt by RT into dou Ya by dou Z. This will be is equals to your dou Ca by dou Z. Clear? So now you must be having a clear idea like how to convert from concentration to gaseous phase mole fraction. So we converted from concentration to gaseous phase mole fraction. How to convert? You have understood. First convert concentration to partial pressure, then from partial pressure to mole fraction into total pressure. Okay, like this. So just put it. So it is just Pt by RT and into dou Ya by dou Z. Now nothing is there, just derivate it. Sorry, just integrate it. So Na into dou Z will be is equals to minus Dab into Pt by RT. All these are constant terms, and dou Ya divided by 1 minus Ya. Now you integrate it from point Z1 to Z2, and here from Ya1 to Ya2. Like what we are considering, please understand. We are considering, suppose this system we consider, and suppose here we say that from here the ammonia vapor is getting diffused in this side. Okay. From here our Na is getting diffused into our B. Here entirely B is present, that is air is present. Okay. So suppose we consider this as our point 1, this is our point 1, and this is our point 2. Okay. The distance from starting point to here is like Z1, and the distance from starting point to here is our Z2. Clear? Like this. And like let the mole fraction at Z1 be Ya1, the partial pressure be Pa1, concentration be Ca1, the mole fraction here be Z, like the distance is Z2, no? So mole fraction is Ya2, the partial pressure is Pa2, the concentration is Ca2. All these things we have defined. Okay. So like what is going to happen is that like suppose you keep like you suppose you keep your ammonia here. Okay. So just in the nearby region, the concentration or the partial pressure or the mole fraction of your ammonia will be high. Now as the distance goes on increasing, we travel far, so this mole fraction will go on decreasing. Getting it? No? Suppose here your Ya1 is equals to 0.3. So if you go on decreasing that, like go on increasing the distance, here your Ya will be is equals to 0.1. Suppose you go more far away, so this here the distance will, like it will become, mole fraction will become, let it be 0.05 more far away. So as we travel far, well, like travel far from the from your ammonia, the point where the concentration is originating, or for the point from where the vapors are originating, your mole fraction as well as the partial pressure as well as the concentration, everything will go on decreasing. Okay. Now just integrate it, and you will get the formula that your Na is equals to Dab into Pt by Rtz into ln 1 minus Ya2 divided by 1 minus Ya1. Okay. This is the first formula that you will be getting. Okay. What is Z? Your Z is nothing but Z2 minus Z1. Okay. That is, the Z is just the distance between these 2 points. Distance between these 2 points is your Z. So Z2 minus Z1 will give you your Z. Clear? So this is one form of representation. Like this, if you go on changing your the values, like this is the formula when you are representing it in terms of gaseous phase mole fraction. Now suppose you want to represent it in terms of partial pressure. So what to do? into PT by RTZ into ln. So in terms of partial pressure, so partial pressure just multiply in the numerator and the denominator by total pressure. So this will become Ya2 into PT and again PT minus Ya1 into PT. So this will just get converted into DAB into PT by RTZ and into ln PT minus PA2 bar and PT minus PA1 bar. Clear? Now suppose you want, this is second representation. Now suppose you want to represent it in terms of concentration. So how to represent it? So DAB, what is concentration? Total pressure divided by RT. So this will give you CT, total concentration, and into ln. Okay, so total pressure will be again equals to CT by RT. Partial pressure will be is equals to CA2 by RT. This will be again CT by RT, and this will be again CA1 by RT. So RT will cancel out, and you will get a formula DAB into CT by Z into ln CT minus CA2 divided by CT minus CA1. Clear? Okay. Now suppose you want to represent it in terms of liquid mole fraction. So your Na will be is equals to DAB into CT by Z and into ln. Again, divide the numerator and the denominator by your total concentration. So this will become 1 minus XA2 and 1 minus XA1. Okay. So I hope now you have got the idea that how to convert between your concentrations, between your partial pressures, between your mole fractions, all these things. So these are the four representations of the formulas that you get from here. Okay, like for diffusion of A through non-diffusing B. I share with the PDF. Like yesterday I didn't share. So today entire diffusion after this is complete, then I'll share you the PDF. Okay. So you can make your notes from there. This thing is clear, no? Okay. If this thing is clear, then one more concept is there. Let us understand that concept. Okay. Let us understand that concept. So this concept is known as, in representing the same formula, we will be representing the same formula in terms of your logarithmic difference. Okay. Like the same formula we will be representing in terms of logarithmic difference or logarithmic mean. What is your logarithmic mean? So how many kinds of mean are there? There is arithmetic mean, geometric mean, okay, and your LM is also there. So what is LM? Let us understand. Suppose you are having two quantities, okay, K1 and K2. So what is arithmetic mean? It is K1 plus K2 divided by 2. What is geometric mean? It is root under K1, K2. And what is logarithmic mean? It will be K2 minus K1 divided by ln K2 by K1. Okay. So this is known as your logarithmic mean. So for any two quantities, you can find out three means. That is your arithmetic mean, geometric mean, and your logarithmic mean. Okay. Now let us understand. So suppose you are having a system like this, and you say that diffusion is happening from point 1 to point 2. Okay. Here it is Ya1, Pa1. Here it is Ya2, Pa2. Now this is for component 1. No. From here, suppose the vapors of component A is generating. Sorry, component A. And this entire place, suppose it is filled up with your component B. Clear? And let our component B be air. So now what is happening is that at point 1, if there is some partial pressure of your component A, then there must be some partial pressure of your component B also. Because if there is some mole fraction of your component A, then component B will also have some mole fraction. No. Similarly, at point 2, if you are having partial pressure of component A, then similarly partial pressure of component B will also be there. Getting it? Now please understand, the total pressure at any point in this system will remain constant. So let PT be our total pressure. The total pressure at any point in this system will remain constant. Pressure is not going to change. Okay, we are considering constant pressure. However, the composition, like it may happen that at point 1 PA1 is high and PB1 is less, and at point 2 PA2 has decreased as because the distance has increased. and PB2 has increased. However, the total pressure, that is your sum of PA bar and PB bar, this is your constant. So from here, what you get is that, from here what you get is your PA1 bar plus PB1 bar will be is equals to total pressure, and that will be equals to your PA2 bar and plus PB2 bar. Okay, so this is the representation. This is the representation of your total pressure. From here, you can also write that PA1 bar minus PA2 bar will be is equals to PB2 bar and minus PB1 bar. Clear? Okay. Now let us understand. So in this equation we were having that our Na, in this equation we were having that our Na was equals to DAB into PT by RTZ and into ln PT minus PA1, sorry, PA2 bar divided by PT minus, sorry, PA1 bar. Clear? Okay. From this equation you can write that PT minus PA2 bar, you can write it as PB2 bar, and PT minus PA1 bar will be nothing but your, sorry, PB1 bar, nothing. We have just considered this equation once and we have just considered this equation once. You're getting it, no? We have just considered this equation once, and once we have considered this equation. From this equation, we have sent your PB2 bar, that's, sorry, PA2 bar this side. So we have got PB2 bar. And from this equation, we have sent your PA1 that side. So we have got PB1 bar. Okay. So now let us make the changes in this equation. So this will become DAB into PT by RTZ into ln PB2 bar divided by PB1 bar. Okay. Till here it is clear. Now let us multiply the numerator and the denominator by your PA1 bar minus PA2 bar and divided by PA1 bar minus PA2 bar. So with the same quantity we are multiplying, so it should not create a problem. Okay. It will just cancel out among each other. And from here, we have also seen that our PA1 bar minus PA2 bar is your PB2 bar minus PB1 bar. So we can put it here. We can put it here. So this will now become DAB into PT by RTZ into ln PB2 bar by PB1 bar into PA1 bar minus PA2 bar, and divided by, this will become PB2 bar minus PB1 bar. Okay. So now this will become DAB into PT by RTZ into PA1 bar minus PA2 bar and divided by PB2 bar minus PB1 bar divided by ln PB2 bar by PB1 bar. Clear? This concept is clear, no? Nothing is there. We have just written it in the denominator. So this part will go up. You know, no? Suppose you have 2 divided by 1 by 3. So what happens? This you can write it as 6. This 3 will go up here. So the same thing. This will go up here, and this will represent the same formula. And from here, now can you say that this quantity, this is nothing but PBLM? That is logarithmic mean of your partial pressure of your B. Logarithmic mean of the partial pressure of B. Just now we have seen, no, that your logarithmic mean is K2 minus K1 divided by ln K2 by K1. So from here this formula becomes, Na is equals to DAB into PT by RTZ and into PA1 minus PA2 and divided by PBL. Similar manner, you can represent it in other terms also, like Na is equals to DAB into PT by RTZ and into YA1 minus YA2 divided by YBLM. You can represent in terms of concentration also, DAB into CT by Z into CA1 minus CA2 divided by CBLM. and Na is equals to DAB into CT by Z into XA1 minus XA2 divided by XBLM. Same thing, just other representations. Okay. So total this many formulas you will be having for your first case. That is your diffusion of A through non-diffusing B. For the first case, you are going to have this many formulas. Clear? This thing is clear? So this conversion, if it is clear, no. So all the formulas, like if you remember one formula, you can go from one. Like this formula, no. This conversion, like how to convert from CA to PA bar, from here to YA, okay, from here to XA, all these things from here to here, vice versa, all these things. Like if these conversions are clear, so you can all, if you remember one formula, the rest of the formulas you can directly write it. Okay. So this was our first case. Okay. Now one more thing is there. So for the first case, I have derived it like this. For the rest two of the cases, I'll just write down the formulas. Okay. Or else our time will not permit. For the rest two cases, like for equimolar counter diffusion and unequimolar counter diffusion, I will just write down the formulas. So as because it was the first case, so I just like a little bit of derivation I did, so that the idea from where like we are getting the formulas, that is clear to you. Okay. Chalo, we can now move forward. One more important thing is there, that is your concentration profile. Concentration profile. So how will be the concentration profile of these things? Okay. So let us understand. So what is the formula that we got for your diffusion of A through non-diffusing B? It was Na is equals to minus DAB into, suppose, PT by RTZ. No, sorry. Yeah, Z was not then. Yeah, PT by RT and into dou YA divided by 1 minus YA, and also one dou Z was there. Okay, like this. So please understand that these derivations that we are doing here, we take an assumption for all the three cases. What are the assumptions? First is your constant temperature and pressure. Constant temperature and pressure. That's why we took our constant total pressure to be constant. Okay. The second is your area is constant. The second is your area is constant. Now, if area is constant, this area is known as your diffusion area. Okay. Like your diffusion area is constant. Diffusion area is constant means, suppose you keep a beaker. Okay. So what is the diffusion area here? The diffusion area here will be this, like this cross-sectional area of the beaker. So now this is the constant only, no? This is the radius is not changing, as because it is a cylindrical beaker. Okay. So like this, it is said that it is a like the diffusion area is constant. Clear? So this thing is there. So if the area is constant, please understand, if the area is constant, then our flux into area gives you rate. Okay. Flux, we are denoting it by Na, and let area be anything like area only. So this will give you rate. So if area is constant, so can we say that our Na, that is equals to our rate by area? If our area is constant, then rate is the constant only. We will get a constant formula only. So our Na will also be constant. Clear? So now if our Na is constant, so you know, if any quantity is constant, so if you do derivative of that quantity, like dou Na by dou Z, that means dou Z of minus DAV into PT by RT dou Z into dou YA by 1 minus YA. This thing. Now as Na is a constant term, so derivative of a constant term will always be equals to 0. So this quantity derivative, if you do, it will be equals to 0. Okay, isn't it? No, this thing is clear. No, that as Na is constant, as why Na is constant, because our area is constant. As because area is constant, diffusion area is constant, so our Na is constant. So if Na is constant, the derivative of a constant term is equals to 0. So dNA by dz will be equals to 0. Clear? So this quantity is equals to 0. So now how to do it? You will integrate it. Once if you integrate it, okay, let me write it again. So dou z of minus dab into pt by rt 1 minus ya and into dou ya by dou z. This is equals to 0. So once you integrate it, once if you integrate it, you will get it. Like these quantities are constant only, so you can directly put it equals to 0 by taking it that side. So the only thing you will be left with is like integration of dou z and dou ya divided by dou z. Okay, and 1 by 1 minus ya, that is equals to 0. You will be only left with this. Clear? Now if you integrate it, suppose you want to integrate it both sides. So if you integrate it both sides, so you will be getting dou ya by dou z into 1 minus ya and equals to c1, where c1 is constant of integration. So once you have integrated it, okay, if you now what will happen is that dou ya by 1 minus ya, that will be is equals to c1 into dou z. Now you integrate it again. If you integrate it again, so what will we be getting? Ln 1 minus ya and minus, that will be is equals to c1z and plus another constant of integration, that is your c2. So this, now here you just put, for finding out your c1 and c2, what you will be doing? You will be putting boundary conditions. Please remember, if you have any equation in this term where you are having constants, so for finding out the values of the constant, we put boundary conditions. Boundary conditions. Boundary conditions here will be that at z is equals to z1, at z is equals to z1, our ya is equals to ya1. So this is one boundary condition. Another boundary condition is at z is equals to z2, our ya is equals to ya2. From these two boundary conditions, you put it here and you find out the values of your constants like c1 and c2. From one boundary condition, you will get constant value 1, and from another boundary condition you will get the, like, the number of constants must be equal to the number of boundary conditions. Okay, only then you will be able to find out the value of all the constants. Clear? What I'm telling you is correct? No. For like number of constant must be equals to the number of boundary conditions you are having. Only then you will be able to find out the total number of constants. Okay. So from here you just find it out the values of c1 and c2, that you do it on your own. Okay. After you do it, then from here, like, the concentration profile will be like, you can directly see the relation. What is the relation between ya and z? So this is a exponential relation. This kind of relation is known as your exponential relation. Like, it is logarithmic, but we don't say logarithmic, we call it exponential. Clear? So that was the derivation of the, like, everything. This, if you now just put the boundary conditions and you derivate, no, like, if you find out the values of your c1 and c2, so you will get a, like, wait 1 second, you will get it in this term, like 1 minus ya2 by, sorry, yeah, like 1 minus ya minus 1 minus ya1 will be is equals to 1 minus ya2 by 1 minus ya1 whole to the power z minus z1 divided by z2 minus z1. Okay, like this you will be getting something like this. So this is the concentration profile. And how will be the concentration profile? It will be like this and like this. This is your pb1, this is your pa1, this is your pa2, and this is your pb2. So please understand what is the significance of the concentration. This is your point number 1, this is your point number 2. What was our system? That our ammonia vapors were diffusing into our air. Our air was non-diffusing medium, that is our B, and our ammonia, that is A, is diffusing. This was our point 1, this was our point 2. This was our point 1 and this was our point 2. Now from here, please remember these things. Okay, please understand concentration profile, how to find out that what is said in the concentration profile. Please understand, this ammonia vapor will start diffusing from here. Okay, very good. However, the entire room is filled up with air only, no? So at any point the amount of air will be higher. Suppose you take a spray like body spray. So body spray you spray in the room. Okay, so the body spray will you spray in the room. So the point where you are spraying, there the smell will be more. Okay, like the body spray, the spray amount, the scent amount, the scent molecules will be more. However, the air molecules will be higher. No, as because the entire room was initially covered with air only, is filled with air only. So even if we are considering point one also, there also the partial pressure of A will be less than the partial pressure of B. That is true. That will be there. However, as we move from point one to point two, now as this distance increases, so as this distance increases, what is going to happen is that the number of like molecules of your number of molecules of your component A, like for this instance, the scent. So this scent will go on decrease. So the partial pressure will decrease till Pa2, and the partial pressure of your A will, or like partial pressure of your B, like for the air, it will increase to Pb2. Clear? So that is the physical significance. You can just simply take an example of that scent. Like if you suppose you sit in one corner and you spray the scent, so around you the like you will get a very high concentration of the smell. But that doesn't mean that more than air the scent is present. No, the air is always higher. So that means your PB will be always higher than your PB1. Sorry, PA1. Okay. But as the distance increases, like from your corner to the other corner of the room, the amount of scent will go on decrease and decreasing, and the amount of air will go on increasing. Okay, so like this. And this decrease and the increase, these concentration profiles, they are exponential profiles. Why they are exponential profile? Because in the relation we are having ln. Okay, so hope so these derivations are clear. Now I'll expect you to do the derivations on your own for your equimolar counter diffusion and for your unequimolar counter diffusion. Okay, then we can discuss it tomorrow. No, we can cover some other topic today. Okay, we can cover some other topic today, and we can discuss it tomorrow. Then we will tomorrow we will solve some questions also based on this. Okay, so I'm just writing the conditions. You do the derivations on your own. Okay, I'm just writing the conditions. Like what are the conditions? Please understand. So for the second condition, that is your equimolar counter diffusion. For your equimolar counter diffusion, we say that our Na will be is equals to minus Nb, or our Na plus Nb will be equals to 0. That means your Nt is equals to 0. So how this is happening? Suppose you are having it like this. Okay, suppose like this a channel is there. Suppose like this a channel is there. Here your bulk A is present, and here your bulk B is present. Bulk is present means, like suppose in your room bulk air is present, means any quantity which is present in huge amount of form or in excess, that we call it bulk. Okay, bulk gas, like this, bulk liquid. Okay, so bulk A is present here and bulk B is present here. Now A will start diffusing in the direction of B, and as because here the low concentration of A is there, and B will start diffusing in the direction of this, as because in this direction the B concentration is left. So high concentration to low concentration B will diffuse, and high concentration to low concentration A will diffuse. So both Na and Nb are diffusing. However, the directions are different. So we are putting a negative sign. Clear? This is your equimolar counter diffusion, and both these are diffusing in the same amount, like the molar amounts, no, that we are considering to be same. So that's why we are considering equimolar counter diffusion. So just apply it to the general equation and derive it in the same way we derived it for diffusion of A through non-diffusing B. Okay, and what is your unequimolar counter diffusion? Unequimolar counter diffusion. So what is unequimolar counter diffusion? Suppose now it is A gives like this kind of thing is there. So minus Na. So let us take plus Na only. No? Yeah. So Na will be is equals to minus Nb by 3, like this. Now they are not diffusing in equal amounts. So now they are, it is not equimolar. It is unequimolar. So like this kind of relation you will be getting. Let us consider the small a to small b. So like this, A by A will be is equals to minus Nb by B. Okay, like this. So like this you will be having. Clear? So from here again apply the same conditions in the, like for here for unequimolar counter diffusion, the derivation will be a little more complex. So tomorrow you try to do the derivation on your own. If you can't do the derivation on your own, then we can just do it, look into it tomorrow. But however, you try it once. Nothing, just apply the same conditions, like this condition into the this general equation of mass transfer, and you try to derive all the formulas. Okay, You derive the concentration profile of of equimolar. No need to derive the concentration profiles and all for the unequimolar. However, it will be same. Like if you want to derive, you can derive. You will get exponential. Okay. So till here, the basic idea of diffusion, I think it is over. Okay. Like the basic idea of diffusion, I think it should be over. Now, what we can do today? 10 minutes are left. Mm, okay. You always also remember one more thing, that your this no that your JA, like what I'm trying to tell is that suppose you are having, this is a binary, we are doing everything for binary, no? So A and B. So you will get one JA, you will also get one JB. So always remember that your JA plus JB will always be equals to 0 for any condition. Why this? Suppose for now, just now we derive no for like for diffusion of A through non-diffusing B. So your Na was equals to Nt into Ya and plus Ja. Your Nb will be is equals to Nt into Yb and plus Jb. Just add them. So your Na plus Nb will be is equals to Nt into Ya plus Yb and plus Ja plus Jb. Okay, this we can do now. We have just added two equations. Nt. This is Nt. Yeah. Now for diffusion of A through non-diffusing B, you know that your Nt is equals to Na plus Nb and your Nb is equals to 0. That means your Nt is equals to Na. So just put it, Nb is equals to 0. So your Na will be is equals to Na into, now Ya plus Yb, sum of mole fractions is always equals to 1, as because this is a binary mixture. So 1 and plus Ja plus Jb. So this will cancel out and this will become 0 here. So Ja plus Jb is equals to 0. Okay. Similarly, you do it for equimolar counter diffusion. See, you will always find that Ja plus Jb will come out 0 in that case also. Okay. So your Ja plus Jb is always equals to 0. Okay. This is one thing. Another thing, you do one thing. You consider DAB. DAB means diffusivity of A with respect to B, and DBA. This is diffusivity of B with respect to A, or diffusivity of B in A. This is diffusivity of A in B. Okay, these two. You try to derive this, that DAB will always be equals to DBA. This also you try to derive at your in home. Okay, very simple. You just take two formulas again from start from here. Put JA is equals to minus DAB into dou CA by dou Z, and put JB is equals to minus dBA and into dou CB by dou Z. Okay. From here, convert this CA into like your XA or YA, anything, and convert this CB into XB or YB, and then add these two equations. So from here, you will get that your DA and DBA will be equal. Okay. So these are like very basic things. You must be knowing it, or else these things may like create confusion. Okay. So till here it is over. No. Chalo. So without wasting time, let us do these derivations. If you tomorrow, I will just write down the formulas, so it will be better. You try the derivations, and tomorrow we will write down the formulas. Okay. Let's not waste time today. Like if you try it on your own once, then it will be better for your part. Okay. Let us now move forward. So till now we were considering that our diffusion area, we were considering it to be constant, isn't it? We were considering our diffusion area to be constant. What if this diffusion area is not constant? What will be the examples? Suppose you have a cylinder. So if in this cylinder the diffusion is happening through the cross section, like the opening, then it is constant, no problem, because the cross sectional area will be always constant, isn't it? But however, suppose now what is happening is that the diffusion is happening in the longitudinal direction or in the axial direction. This distance is known as your longitudinal direction. Okay, this is longitude, no? So in the longitudinal direction. Now in the longitudinal direction, what will happen? You are getting it, no? Like this is, suppose this is the cross section. Suppose this is the cross section of your cylinder. So as this is going on, like diffusing, the area also changing, because the area is the curved surface area. The curved surface area is 2 pi rl. So as r will change, r is going on change, no? Like from here to here, let r be 1 centimeter. From here to here, r will be 2 centimeter. From here to here, r will be 3 centimeter. From here to here, r will be like 6 centimeter. Suppose in this some distance is there like 5 centimeter. Okay, so this r is continuously changing. If r is continuously changing, then your curved surface area will be continuously changing. And curved surface area changing means diffusion is happening through the curved surface area only. So now the diffusion area is not constant. Clear? So this is one example. Suppose you have a sphere. A sphere is there. Okay, this entire sphere is there. So in this sphere also, suppose from the center of the sphere, it is diffusing. So again, the radius is going on changing. And what is the area of the sphere? 4 pi r square. So as r is continuously changing, so the area of diffusion will continuously change. Okay. So these are the two examples. Like many more examples can be taken up, but we will understand that how to solve this question just based on these two examples only. Okay. Now please understand, we were dealing with our flux. So let Na be our flux. Okay. We say that if we multiply this flux with area, then we get rate. Always remember that rate is always constant. Rate is always constant. What changes is flux, because flux depends on area. Flux is what? Rate by area, no? So rate is always constant. However, if this area is variable, then your flux is variable. Clear? So flux may vary. However, rate will be always constant, and depending on the area, whether the area is constant or it is variable, our flux will be variable or it is constant. If area is constant, then flux will be also constant. Just now we saw the cases. However, if area is variable, then our flux will be variable. So in that case, how to like approach the problems? So what is going to do? Let us consider for the case of cylinder only. So for cylinder, suppose we take Na and into area. That is your rate, and this is equals to constant. Let your Na at radius 1 be your Na1, and the area is 2 pi r1l. So this will be is equals to constant, no? So we can take it as Na2 at radius r2 and into 2 pi r2l. The l is constant, length is constant. 2 pi and l will cancel out. From here you will be getting Na1 r1 equals to Na2 r2. Clear? So Na1 by Na2 will be is equals to R2 by R1 directly. This is for cylinder. So now for sphere, I think you can do it automatically on your own. For sphere, what will happen? For sphere, what will happen? Your Na1 into, what is the area 1? 4 pi R1 square. Similarly, Na2 into, what is the area? 2. 4 pi R2 square. 4 pi will cancel out. You will get Na1 by Na2 is equals to R2 square by R1 square. From here, very basic problems comes. Okay, it has came in GATE PYQs also. What happens is that they say that an naphthalene ball is there, and suppose at a distance 3 centimeter, the flux is like 5 mole per meter square second, and so at a distance of 9 centimeter or from the center, what will be the flux? Na2. So you can use this approach directly. You can calculate it. Getting it? No? Like an naphthalene ball will be given. It is said that from the center at a distance of 3 centimeter, the flux is 5. So at a distance of 9, how much will be the flux? So very simple. Na2 by Na1 will be is equals to R1 square by R2 square. What is R1? That is 3 square. And what is R2? That is 9. So 9 square. So your Na2 will be is equals to 5 into 3 square by 9 square. So like this, very easily you can solve these questions. Okay, so this was the concept of diffusion through varying area. Okay, one more PYQ question has also come. So you can check it from there also. Okay, like what is going to happen is that, please understand, what is going to happen is, suppose it is said to you that you write this, like your like one question was there like this. Okay, like let me remember it. Yeah, suppose our first term. At least like this, a first term is given. Okay, it is said a liquid is contained in it, and these liquid vapors are diffusing into the air. Okay, so you have been said to find out that find out the expression like what to say, the like your Na. What will be your Na in this case? We can use normally, no, dab into, suppose, into Ct by Z. Sorry, yeah, dab into minus dou Ca by dou Z, and here we can put 1 minus Xi. Okay, like this, like we are writing it in terms of your liquid mole fraction, nothing else. So this is your flux. Okay. Now what will be the area in this case? So what was this was the confusing part. So see here the area. See here very carefully. The area. This area is changing. This area is changing. It is a first term. So as we are moving from top to from like the bottom to the top, the area is changing. However, the final this final diffusion area, this area, the final diffusion area from these vapors are diffusing into the air. This area is constant. No, it can be any shape. It can be like this shape. However, if it is diffusing from here, this area, so this area is constant, no, and it is what, pi r square. But no matter, like suppose some radius was given r, so it is pi r square. Getting it? If it is said that the diffusion is happening in this direction, like in this direction, then the area will be changing constantly with respect to radius. However, it is given in the question that the area, like the diffusion is happening in this direction. So if it is happening in this direction and this is your opening, so if your opening area is constant, that means it is constant, no? So area here will be directly pi r square. So many students got confused here. Okay, so please keep it this in mind. This is pi r square. So directly you multiply this with pi r square. This will convert into rate, and rate is always constant. So you directly write dou z and of your this entire quantity, and that is equals to 0, and that will be your answer. You can find this question in your PYQ. I don't remember the year it has came, but yeah, this question has also came. Okay, okay. So this was the diffusion of your like through varying area. Okay, let us do one more concept. Let us do one more concept. This concept is known as your diffusion of your naphthalene vapor, naphthalene ball. Okay, this concept is known as diffusion of naphthalene ball. Okay, so what is this concept? Let us understand. So naphthalene ball means what? Naphthalene ball you have seen, no? Some white color balls will be there. Okay, so you keep it in the clothes so that the like no insect or in all these things clothes don't like what to say, don't destroy your clothes. Okay, so you keep it in the clothes while storing it in the almirah. Now what happens is that suppose initially the ball size was this, so you keep it. After some days you take it out, you will see that the naphthalene ball has decreased in size. It has become like this small. It has happened, everybody must have seen also white color balls naphthalene, like this packet comes, many naphthalene balls are there. ठीक है, तो इसमें क्या होता है, इस कपड़ा में हम लोग डालते हैं अलमीरा वगैरह में स्टोर करते करते हो ताकि कीड़ा वगैरह कपड़ा में नहीं लग जाए. ठीक है, चाहे मतलब खराब स्मेल ना आए कपड़ा से, क्योंकि बहुत दिन तक स्मेल, जनरली ठंडी का कपड़ा मतलब विंटर, योर विंटर क्लोथ, नो, while storing your winter clothes after your winter season is over, so you'll see your at your home you'll see your parents like putting these naphthalene balls inside the clothes. Now from the next year when you take out these clothes to wear, you'll see that the naphthalene ball size has decreased, it has become smaller. Okay, so now what this happens, why this happens is that the naphthalene, this is naphthalene ball, so the vapors of naphthalene form of vapor, they start diffusing into the air. Okay, they start diffusing into the air, and as they go on diffusing into the air, diffusing into the air, so the amount of naphthalene goes on decreasing and their ball size decreases. Okay, so what here we find out is that suppose, what here we try to find out is, suppose at a distance like at a distance of r1 from the center of the naphthalene ball, what is the flux? Here we find out two things. First thing, at a distance of r1, what is your Na at r1? What is the flux? And the second thing is total time taken. Total time taken for this naphthalene ball to be completely evaporated. Okay, these two things we will find out. Time taken for complete evaporation. For complete evaporation. Like for total time taken for this naphthalene valve to get totally like evaporate, like totally diffuse into the air, so how much time will be taken? Okay, so these two things we find out. So let us see how to find out. So for finding out the like this thing, for finding out the Na at r1, so you can find it out directly. I'm just writing out this formula. because everything, if we start deriving, it will not be possible. So you can remember the formula: Pt minus Pa2 divided by Pt minus Pa1 sat. Okay, so this is the formula for your this flux at your distance r1. Okay, this Pt is the total pressure, r1 is the distance from the center, r1 is the distance from the center. Okay. Okay. What is Pa2 bar? This Pa2 bar. Now see here, understand this concept is important. What is Pa2 bar? This Pa2 bar is the partial pressure at your distance R2. At distance R2. Okay. Like suppose this naphthalene ball you have, no. So we consider a point here that is your R2. So the partial pressure here. So this we neglected. This almost like every time we neglect it. And at R1, that is just at this center, just at this point, just at the radius of the ball, we consider the naphthalene vapors to be present at its saturation pressure. That is your Pa1, like Pa1 sat. Okay, don't put the bar sign here. Don't put the bar sign. Just put Pa sat. Okay, this concept is clear now. What I'm telling, like we say that suppose this naphthalene vapor, naphthalene ball is there, and it starts diffusing. So just at the circumference of this ball, the vapor pressure of like the partial pressure of this naphthalene vapors will be equals to the vapor pressure. You're getting it? No. Just at the circumference, the partial pressure will be equals to the vapor pressure, because it is at the circumference. There it is present in very high concentration. Okay. However, if we increase the distance and we go to a point like R2, at that point we can say that the partial pressure is almost equals to zero. Okay. So that is a catch behind. And this is the formula. This R1 is that, like suppose this naphthalene ball is there and this is the radius of the naphthalene ball. This R1 is that radius. Okay. And this Na at R1 is the flux at your R1. Okay. So this is the Na at R1. And the second thing is the time taken for complete evaporation. So for time taken for complete evaporation, please understand one thing. One formula, another formula is that you remember this formula. It is your Na is equals to minus rho by m and into dr by dt. Okay. This formula we get it by just simple like unit balance. What is the formula for this? Mole per meter square second. No. What is the formula for density? Let it be kg per meter. Let it be kilomole. What is the? This is m is molecular weight. This m is molecular weight. So what is the unit of molecular weight? It is kg per kilomole. What is dr? Meter and time second. So kg will cancel out. You will get kilomole per meter cube into meter per second, meter square. This will become kilomole per meter square second. So just by unit balance, we can represent our flux in this formula also. That our Na is equals to minus rho by m into dr by dt. Clear. So with this we start our derivations, and from here we get our final formula that our Tf is equals to rho r1 divided by 2m and into 1 by Na at R1. Okay. So this TF is the final time or the total time taken for complete evaporation. For complete evaporation. Okay. So rho R1 divided by 2m. This like rho into R1, density of the naphthalene into R1, that is the the radius of the ball, divided by 2 into molecular weight and into 1 by Na at R1. That what at this distance R1, what is the flux? So this will give you the total time taken for complete evaporation. Okay, so this was all about your diffusion. Next, for tomorrow, we will start our absorption and stripping. Mass transfer coefficient, that part is left. So that part we will cover. I'll see, like if tomorrow it is possible, then we will cover tomorrow. Or tomorrow, let us solve some questions on this diffusion. Then we can start absorption and stripping. Okay.